We often think cutting-edge tech means, the latest phone or some web thing.
Right, the tangible stuff.
But maybe the biggest leaps, the real game changers, are happening in places like quantum physics and space exploration.
Exactly. Fields that sound almost like science fiction. That's where those unexpected aha moments often come from.
And that's what we're diving into today based on the really great sources you, the learner, provided.
Yeah, the plan is to unpack some key developments in quantum information science, QIS, and space exploration.
And see how they connect, right? How something like optimizing, I don't know, shipping routes
Right.
could somehow relate to getting humans to Mars. It seems wild.
It does, but the connections are definitely there.
Okay, so source number one, the 2024 Quantum Information Science Applications Roadmap. This comes from the Department of Energy based on expert interviews.
And their long history in the field, it's worth noting. So
Yeah.
it's grounded.
Grounded, yes. But it also stresses, look, the science is moving fast, but the actual tech, still early days, lots of research engineering hurdles remain.
Definitely. And it highlights something critical. Quantum tech doesn't advance alone. It needs breakthroughs in materials, systems engineering, even just how you package these super sensitive things.
Right, like one breakthrough could ripple out.
Precisely. Then there's the Global Exploration Roadmap 2024.
This one's huge. A collaboration, what, 27 space agencies?
Yeah, under the ISEG,
Yeah.
NASA, ESHX, Roscosmos, CSA, loads of them. You see the logo?
It really shows this global push for space, cooperatively, sustainably.
Expanding human and robotic presence out there. The scale of the cooperation itself is pretty remarkable.
But a united front, almost.
Yeah,
And our third piece, the Google AI blog from 2024.
right. A year of extraordinary progress. It covers their new Gemini models, generative AI, robotics, the usual suspects.
But crucially for us, it also mentions quantum computing breakthroughs and how AI is digging into science itself.
Yes, they see AI as an accelerator, a tool to push forward in fields like quantum. It's not just a separate thing.
Okay, so let's connect these dots. That's the mission here, isn't it?
Yeah. Find the surprising intersections, how quantum impacts space, how AI fits in, give you that shortcut to the bigger picture.
Without getting totally lost in the weeds.
Hopefully. Let's start with quantum sensing. It sounds technical, but the idea is, well, it's kind of revolutionary.
Not just better sensors, you mean?
Not just incrementally better, no. It's using quantum information science insights for a fundamentally new way to measure things.
Okay. How? The roadmap mentions qubits.
Exactly.
Yeah.
Using qubits, those quantum bits, they can be 0 and 1 at the same time as the sensor itself.
Right, superposition.
That allows for incredibly precise measurements. Think atomic clocks, but even more accurate. Huge implication.
And not just clocks, right? The roadmap mentioned imaging. Tiny things.
Yeah, high spatial resolution,
Yeah.
microscopic probes. They show an image, figure 3.1b, of a nitrogen vacancy center in diamond,
Yeah.
basically a specific type of qubit. Imaging a protein. Think MRI, but way, way smaller scale. For materials, science, chemistry, biomedicine. Pretty exciting.
And they work in tough places.
Some of them, yeah. That's another key point. Certain qubits are surprisingly robust. They can handle extreme environments, deep underground, vacuum of space, even near hot plasmas,
Which is obviously crucial if you want to stick a sensor on, say, another planet.
or deep inside a fusion reactor, for instance. Now, here's the really cool part. Beating classical limits.
The standard quantum limit, I saw that in the roadmap.
Classical sensors have this fundamental noise floor, a limit to their precision. Figure 3.1a shows it like a fuzzy circle minimum uncertainty.
Okay, you can only get so precise.
With classical methods, yes.
Okay.
But quantum sensing can get around that. The other side of that figure shows squeezing.
Squeezing.
You sort of redistribute the uncertainty. You make the measurement noisier in a way you don't care about to get super precise measurement in the variable you do care about.
Like focusing your measurement attention.
That's a good way to put it. And this isn't just academic. Surpassing that limit, it opens up new windows on the universe.
Like seeing things we couldn't see before.
Potentially, yes.
Yeah.
The roadmap mentions detecting single photons, which could be key for finding dark matter candidates like axions.
Whoa, okay. Axions?
Or even detecting the direction of other dark matter particles, WIMPs, using solid-state quantum sensors. It's about accessing phenomena that were previously below the noise floor.
So brand new eyes on the cosmos, essentially.
That's the promise. But as the roadmap stresses, making this happen needs teamwork. Figure 3.3 shows it. Physicists, engineers, material scientists, all working together.
Interdisciplinary is the word. Okay, that's sensing. What about another angle? Optimization.
Right, another huge area for quantum information science.
Yeah.
Optimization sounds maybe a bit dry.
Compared to dark matter, maybe?
Fair enough. But it's everywhere.
Yeah.
Scientific discovery, supply chains, shipping routes, power grids, manufacturing, finding the best way to do something complex.
And the problem is, it gets complicated fast.
Extremely fast. Add more variables, and the number of possible solutions just explodes exponentially. Classical computers, even supercomputers, really struggle with the biggest optimization problems.
Okay, I see the problem. How does this tie into space, then? The Global Exploration Roadmap.
Yeah, think about running a moon base. Seriously.
Okay. Supplies, crews, schedules.
Exactly. Coordinating deliveries, maintenance, experiments, maybe multiple international partners. The logistics are incredibly complex.
Way beyond routing a few trucks.
Absolutely. The quantum roadmap talks about quantum computing potentially revolutionizing how we manage infrastructure, logistics, commerce.
On Earth, mainly, in their examples.
Yeah, the examples are Earth-based, but the principle of optimizing these massive, complex systems, that's directly relevant to space exploration. Scheduling launches from different agencies, planning trajectories, managing resources across the solar system.
Problems that would choke a normal computer.
Or take it years to find just an approximate solution. Quantum computers, if they scale and become robust, might find the truly optimal answer much, much faster, making long-term space presence more feasible, more affordable.
A superpowered logistics brain. Got it.
Now let's switch gears again. Quantum networks. And entanglement.
Ah, the spooky stuff.
The spooky stuff. Entanglement particles linked, influencing each other instantly, no matter how far apart. The roadmap mentions the Bell tests, the Nobel Prize. This is real, experimentally verified weirdness.
So how does that help build a network?
Well, classical networks just send bits back and forth, right?
Yeah.
Quantum networks, especially ones using shared entanglement, can do things impossible classically.
Yeah.
Like quantum teleportation
Teleportation.
of quantum states, not people.
Yeah.
It's still amazing. And even without entanglement, quantum networks offer things like quantum key distribution for ultra-secure communication.
Okay, but getting entanglement to stretch over long distances, that's hard.
Very hard. The roadmap points out transmission loss is a killer. The quantum state degrades.
So how do you fix that?
One technique mentioned is entanglement swapping. Think of it like quantum relays. You create entanglement over shorter links and then swap it to create entanglement over the full, longer distance.
Clever. So what's the payoff? What can you do with a long-distance quantum network?
Here's a mind blower connecting back to space. Linked telescopes.
Link telescopes with entanglement.
Yeah. Figure 4.2 in the roadmap illustrates this. By linking telescopes quantumly, you can dramatically boost their effective resolution, like creating a virtual telescope the size of the distance between them.
Whoa. How much better?
The roadmap suggests we could potentially see, like, 15-meter features on Pluto from Earth.
15 meters on Pluto. That's incredible. Way beyond what we can do now.
Far beyond single telescopes or even standard radio arrays. And they also mentioned using quantum memories, ways to store quantum states at satellite locations, could help see really faint objects too.
So entanglement links telescopes, like it links particles, giving us this super sharp view.
That's the analogy, yeah. A magnified view of the universe, thanks to quantum mechanics.
Okay, quantum sensing, quantum optimization, quantum networks for astronomy. Where does AI fit into all this? Let's bring in that Google blog.
Right. Google's making huge strides. Gemini 2.0, integrating AI into products.
They mention Notebook LM's audio overviews, AI hosts discussing documents.
A bit meta, given what we're doing.
Yeah.
But beyond that, the blog highlights AI tackling really hard science. AlphaFold 3 for protein structure prediction, AlphaProteo, nanoscale brain mapping.
Okay, protein folding, brains. How does that help us get to Mars? Seems like a leap.
Maybe not such a big leap. Think about the global exploration roadmap again, long space journeys.
Yeah.
What happens to the human body?
Right, radiation, microgravity, major challenges.
Exactly. AI like AlphaFold, designing proteins more accurately. That could lead to better drugs for astronauts, maybe more efficient life support systems based on biological processes. Understanding the brain changes in space through detailed mapping, crucial for crew health and performance.
Okay, I see the connection now. Biological challenges. What else from the AI front? Reliability.
Yes. The Google blog mentions their FCTS grounding benchmark, basically, making AI more factual and reliable.
And that's important for space because...
Autonomy. As we go further out, real-time control from Earth isn't possible. We need reliable autonomous systems, The ISECG roadmap specifically calls out assessing autonomy gaps.
So robots exploring Mars